Let's walk through some of practice set 9, where we get some practice implementing some tree-based models, some of the most powerful predictive analytics models that we can be doing in predictive analytics. So we'll start out by looking at the churn data set, and this is a problem that many telecommunications companies deal with. We have a set of customers, and some of them are going to renew their contracts once they're up for renewal, and others are going to churn. They're either going to go to a different company, they might change plans, they're not going to stay with the plan they're currently enrolled in. So our job is to come up with some sort of model that predicts the churn column with the levels yes or no. We're interested in knowing what customers are more likely to churn than others. So because we're going to be doing predictive analytics, the first thing we want to do is to split up our data into a training set and a holdout sample. We're going to set aside the individuals in that holdout sample until the very end, after we've selected our final model, just to make sure that that final model is generalizing about as well as what we expected. So we'll do this randomly. We'll set the random number seed to 2018 so that we all get the same set of randomly picked rows to go in our training sample, and we'll select 70% of the rows to go into training. So we'll define those train rows, we'll put the train and holdout samples as defined, and we can confirm the sanity checks that we are working with the dataset as I intended. So, all right, the first question to ask is, well, what would the naive model do? Basically, what would no model do in terms of its predictions? So what the naive model will do is it'll glimpse inside the training data and look to see, well, what's the distribution of the classes that we're trying to predict. And in this case, the majority class is no, most customers don't churn. And so the naive model is going to predict no for everybody on the training set, on the holdout sample, in the future, etc. So we get some sort of baseline accuracy rate that we need to make sure that any model that we implement needs to beat here. So the estimated accuracy would just be the fraction of individuals on the training data that have that majority class. So we could look at that 3013 out of the number of rows in the training data to get an estimated accuracy of about 86%. How well does that do on the holdout sample? Well, we need to see what fraction of the individuals on the holdout sample had that majority class. If I type in the logical statement, holdout $churn equals no, I get a bunch of trues and falses for whether or not that individual did not churn, or if they did. And so I can look for the average value of this vector, since true is 1 and false is 0. And I find that this model has an 85% accuracy on the holdout sample. 85.3% of the individuals on the holdout sample do not churn. And that's a pretty high accuracy. So I need to make sure that if I am interested in tuning models on accuracy, that my model can actually beat this number. However, what we're probably more interested in doing is having the model select the top individuals in terms of their churn probabilities. We want the 200 most likely customers to churn so that we can intervene, send them promotions, or do something that hopefully prevents them from churning. So what we can do is we can develop the models either or. We can tune the models based on that quantity, the area under the ROC curve, which allows us to tune a model that's more adept at ranking probabilities between individuals, essentially selecting the individuals with the highest probabilities of churning, or we can just stick with the accuracy and tune models based on accuracy. So in this case, it probably makes more sense to tune models based on the AUC, the area under the ROC curve, because we'd probably be using this model to pick out those customers with the highest probabilities of churning. But in this case, what we're going to do is we're going to estimate the generalization error and accuracy of a logistic model from the training data and actually look to see what its actual accuracy and AUC is on the holdout. And we're actually going to tune the models from here on out just to be based on the accuracy instead of the AUC, just for illustration. So because we're going to be calculating the AUC on the holdout sample, I need to load up the proc library as well, because the command in proc to get the area under the ROC curve lives inside that library. So let's load up the caret in the proc library. We're going to set up the fit control object so that we're tuning on the accuracy of the model. Once again, it probably makes more sense to do the AUC, but for illustration, we're just going to tune on accuracy, in which case we say we want cross-validation 5 k-fold cross-validation in fact, and because we're doing probabilities, we're dealing with classification, we're going to add that extra argument class probs equals to true. So how does the logistic regression run? Well, what we do is on the same line as train, because it's estimating the generalization error with the k-fold cross-validation, we want to make sure to set the seed as we run the train algorithm so we get the same estimates of the generalization error from person to person. What are we predicting? We're predicting churn. What are we predicting it from? Everything. So churn twiddle dot. We're always fitting it on the training data. And the method that we're going to pass to the train function is GLM. That's our logistic regression method. And we're estimating it with the k-fold cross-validation. And we're going to do some pre-processing. So we're going to make sure to, as the model is being fit, transform the data so that every numerical predictor has a mean of 0 and a standard deviation of 1. This matters to some models. It doesn't matter to logistic regression, but this just helps the code look consistent from model to model. It doesn't change any of the results. If we do, the center and scaling, so might as well leave it in there. So we'll fit the logistic regression model after, of course, defining fit control, and we can get an idea for what we think its performance might be. So if we look at the $ results component of the object that was created by train, that lets us know what the estimated accuracy is in terms of generalization, and then also the standard deviation associated with that, and even the kappa statistic that we've talked about. So we'd estimate the generalization accuracy to be about 86.5%. With a standard deviation, we think we've nailed that down to about 0.5% here. So how well does it actually do on the holdout sample? Out of curiosity, let's just see. Well, a few ways of going about doing that. First, we need to make predictions on that holdout sample. So the predict command is going to help us out here. We'll predict using the GLM model on the holdout sample. If we just run that, we get a whole bunch of yeses and nos. And so we can ask, well, does the actual value on the holdout sample in the $churn column here, does that equal the prediction? If we print that out, we get a bunch of trues and falses. True is 1, false is 0, so we can ask for the average of this vector. And this will give us the fraction of observations on the holdout sample that were classified correctly, so 86%. Now, if you don't want to type that in manually, the post for sample command in the caret package will do this for you as well. We still have to make the predictions. The first argument are the predicted classes, the yes or no's. The second argument are the actual classes, the yes or no's. And if we ask for a post resample, it lets us know that we have an 86% accuracy on that holdout sample. And this was the kappa statistic on that holdout sample. All right, but what about the area under the ROC curve on the holdout sample? Well, ROC in the PROC package is going to calculate that for us. The first argument in this case are the actual class labels on the holdout sample, so the yeses and nos that are in our holdout sample. And then what we need to give it as the second argument are the predicted probabilities. So let's predict on the holdout sample, but ask for the probabilities instead of the classes themselves. That's what the type equals prob in quotes gives us. If we actually type that out and just run that command, we actually get two columns. We get a data frame of predictions. The first column is going to correspond to the probability of whatever class is first alphabetically. The second column is going to be the probability of whatever class comes last alphabetically. So we actually want that second column. We're predicting the probability of churning. So bracket comma 2, let's just look at that second column. And so we find the area in the ROC curve on the holdout is about 0.83. What does that tell us? Well, it tells us that if the logistic regression model was to make predictions on a person that eventually did churn and made predictions on a person that eventually did not churn, there's an 83% chance that the model would assign a higher probability to the eventual churner than to the non-churner. In other words, it's ranked those probabilities correctly. And that's a good thing. All right, let's move on to the nearest neighbors model, and we're asked to try out values for the nearest neighbors of k of 1 to 25. So make predictions by looking at the closest individual, and whatever that individual's class label was, well, we'll predict that other individual we're trying to classify as that label, all the way up to 25 neighbors. So if we're going to make a classification for a new individual, find the 25 most similar people in the training data, and each of those people will get a vote in majority rules. So What we're going to do is we're going to set up a grid of tuning parameters for the train function to look over. So expand grid, and then letting k equal 1 colon 25 is going to make a data frame with a single column, whose column name is k, and all the values in that column give the values of the tuning parameters that we're interested in auditioning. So we'll left arrow this to k and n grid, and then we'll run the train function, turning on the nearest neighbors model. So same formula, churn twiddle dot, always fitting it on the training data. In this case, method will be knn. We're still estimating the generalization error with the k-fold cross-validation with k equal to 5. And we're still tuning on accuracy. That's how we set it up. Tune grid is letting us know what values of k we're auditioning. And then we're going to center and scale the variables as the model is being fit. And this matters for nearest neighbors. We want to make sure to always have each numerical predictor have a mean of 0 and standard deviation of 1. And adding this argument does that for us automatically. So we'll set it loose, and then we'll look to see how well it did. So just like with logistic regression, if we look at the $ results component of the object created by train, we get a whole bunch of output, in this case a data frame letting us know for this value of k, this is the estimated generalization accuracy, this is the estimated generalization kappa, and the standard deviations of those two quantities. Now, we don't really want to scan through this whole data frame and pick out the row that has the highest accuracy, and so therefore, what we want to do is just print out the row that matters. So turning on the square brackets after this data frame and then saying, all right, let's find the one that had the values for the best tuning parameter. Kn $ best tune tells us that, okay, this was the 5th row. We'll ask for the one of the 5th row here. It lets us know that k equal to 5 looks like it's the optimal choice. The estimated generalization accuracy is a little over 89%. What's the accuracy on the actual holdout sample? Well, we can copy and paste what we had done for logistic regression and find, well, what's the average of the logical vector when we compare the actual values in the churn column to what's predicted by the k nearest neighbors model. Now, the important thing for the k nearest neighbor model is that when we're making predictions, we want to make sure to actually have the set.seed command on the exact same line. Why is this the case? Well, if it happens to be the case that we find that there's a tie in the number of votes for either of the two classes, R is going to pick one of those two classes just at random. So in order to make sure that we come up with the same set of predictions for individual to individual, for student to student, having that set seed there makes sure that the ties are broken in the same manner. So it looks like we get about a 89.7% accuracy on the holdout, a little bit better than expected. What about the area under the ROC curve? Well, the ROC command, once again, extracting out the second column for those predicted probabilities, making sure to have set seed so that each student gets that same answer. We get 0.8401. A little bit better than that logistic regression model. All right, so now let's start to get some practice with our tree-based models. And this is really where it's at in business analytics. Tree-based models naturally incorporate complex interactions into the models, and we see time and time again in business analytics that fairly subtle interactions can play a pretty important role in many real-world relationships. So what we're going to do is we're going to first audition a vanilla partition model, just a single decision tree, and we'll see how well that does. So the tuning parameter with a vanilla partition model is the complexity parameter. Basically, if we're going to add in a new rule to a tree, it needs to improve the tree. It needs to improve that model by quite a bit. That CP parameter is a threshold for how much that new rule has to improve that tree in order to be incorporated into that model. And so what we'll do is we'll audition various values for this CP parameter, and I'm going to write that as 10 raised to a sequence of powers. So if I do this, I'm going to get values of the CP from very, very, very tiny, even the smallest improvement for the tree will be incorporated, to pretty large values of the CP. So a new rule has to really improve the quality of that tree to be considered. I don't know what's going to work ahead of time. We're going to try out all these values and just see what works the best. So we'll define this as R part grid, and this will make a data frame with all those values of the CP that we're auditioning in that column called CP. And then we're ready to set train loose. So since the syntax is so similar from method to method, I'm going to just borrow the syntax for the nearest neighbors model and just change a few things up. So instead of left arrowing it to KNN, I'm going to left arrow it to be tree. Same formula, churn twiddle dot, same training data. The method, though, I need to change to rpart. All right, I'm still estimating it with k-fold cross-validation with k equal to 5. My tune grid, though, well, I need to tune over the values of CP that I've set up. And tree-based models don't care if you center and scale your data. It doesn't care if the mean of 0, standard deviation of 1, but it doesn't hurt. And so, just so I can copy and paste easily, I'll leave it as is. So we'll go through, audition all those values of the CP, and now let's see what works best. So let's look at the $results component of the object that was created. That's 30 different rows. I'm not going to waste my time hunting through to see which one has the highest accuracy. So I'll just extract out the row associated with the best tuning parameters. So it looks like a CP of this value. Looks like it's working the best. In fact, I can see how the performance of the tree is tied into the tuning parameter by making a plot of the object that was created by train. And I see that, okay, smaller values of the CP parameter are a little bit better. I get a little bit of a blip up in terms of estimated accuracy. And then if I decrease the number of rules in my tree by increasing that CP parameter, I see that the performance gets a little bit worse and worse. So too many rules, not as high in estimated accuracy. Too few rules, not as high of an estimated accuracy. There's a sweet spot here that seems to capture the complexity of the tree, the number of rules just right, and it looks like that's associated with a CP of 0.0045. All right, so how well does this do on the holdout sample, just out of curiosity? Well, same sort of deal here. I can just reuse this code. We can look at the fraction of time that the actual values in the churn column on the holdout sample match up to what's predicted. So I'll just change K and N to tree here. And it looks like our estimated accuracy is, pretty darn good, 94.3%. Quite a bit better than the accuracy of the nearest neighbor model. I could get that with the post resample command as well. I could get kappa as well if that mattered to me. What about the area under the ROC curve though? Well, let's just change K and N to tree in this case. We'll extract out the probabilities of churning based on the predictions that the tree was making. And we get a value of 0.8832. So quite a bit better than what the logistic regression was giving us. In fact, let me clean this up a little bit. This was the actual accuracy on the holdout. The estimated accuracy on the holdout was a little bit higher. We expect a little bit of a hit to our accuracy on the holdout sample on genuinely new data, but not a very big decrease. Our model's not overfit or anything. But this definitely looks like it's an improvement over the logistic regression and the nearest neighbor model. Now, one more thing, and this is one reason that we like vanilla partition models, is that we can actually look at our model after we fit it. Now, in this case, what I want to do is manually fit the model with a different value of the CP. This small value of the CP makes a tree that's, pretty darn complex, a lot of rules here, and it's going to be a little bit too hard to make predictions. So what I'm going to do is I'm going to just left arrow into an object called model, the result of running rpart, which is the manual process of fitting a vanilla partition model. Same sort of deal here. We're going to fit the model on the training data, and we're going to say use a CP value of 0.05. So when I do that, that allows me to use the visualize model command from Reg class and look and see what this model actually looks like. Now, so here's the reason why we're using a CP of 0.005 instead of the one that was optimal. If I try to make this model and visualize it, that's a big tree. So if I'm going to do a manual prediction just to remind myself how the prediction actually goes, that's a lot to work with. So we're just going to use a simpler model so we can get some practice making manual predictions with this tree. So the goal here is to make a prediction for the individual in the 10th row of the churn data frame. So here's the information that we know about this individual. It turns out this individual actually did not churn, but let's see what this model makes a prediction. All right, so the way that we make a manual prediction with a partition model is we start up at the top and we ask a series of questions. And depending on the answer to those questions, we head off to the left branch or the right branch. So whenever the answer to the question is yes, we head off to the left. R tells us there's a little yes here on the upper left here. And whenever the answer to the question is no, we head off towards the right. This no here is a reminder of that. So our first question is the value of total day minutes less than 264? So if we look for total day minutes, we find that it's 258.6. So the answer to this question is yes. We head off to the left, and the next question that we're at to ask about this individual is their number of customer service calls less than 4? Well, it's 0 in this case, so the answer to this question is yes. So we head off to the left once again, and now we're asked, is the value in the international plan column for this individual equal to no? All right, well, we'll go and look at the value. We see a value of yes here, so the answer to this question is no. Is the value in their international plan column equal to no? Well, no it is not, because it's equal to yes. So because the answer to this question is no, I'm going to head off towards the right. And now I'm asked to consider the value of total international calls. Is it at least 3? Well, if I find the total international calls here, it's 5. The answer is yes. I head off to the left. What's their value for total international minutes? 11.2. Is that less than 13? Why, yes it is. So I head off to the left once again. So I end up in this leaf of the tree, and what I see is that the model predicts that there's a 1.7% chance the individual is going to churn, and a 98.3% chance that this individual is not going to churn. So it turns out that in this case, the prediction was right. In actuality, this customer didn't churn, and that's reassuring. So 1.7% chance that this customer does churn, and a 98.3% chance that the customer does not churn. And we're even getting a little bit more information here. We have 175 other individuals in the training data that this prediction was based on. So I feel pretty confident in this prediction here. 175 other similar customers, and almost all of them ended up not churning. All right, now let's try out the random forest model. And the random forest model has quickly become more or less the benchmark for predictive analytics models. It's extraordinarily flexible, very powerful, is able to model complex relationships, and it really doesn't require all that much training. So the idea is why hedge all your bets in one prediction model? Why don't you go ahead and create a few trees, in fact, a few hundred trees, maybe even a few thousand, and average the results together? So I guess I should probably say, why put all your eggs in one basket in one tree when you can hedge your bets and actually create a forest of trees and average together the results? So the random forest has one tuning parameter called mtry, and the key to the random forest success is actually in this mtry parameter. So the forest tries to ensure that the trees look as different as possible. So number one, it's creating each tree on a bootstrap version of the training data, basically picking rows at random from the original training data set. So some individuals appear more than once, others get completely left out. So each tree works with a slightly different set of individuals. But that mtry says, all right, if we want to add in a new rule to a tree in that forest, we're going to select mtry predictor variables just completely at random from all the available predictors. So when mtry is equal to 2, we're going to add a new rule to the tree. We randomly select from all the predictors that are available, just 2 of them, and pick the very best rule that we can base on those 2 predictors to add to the tree. So why is that so important? Why does that really contribute to the model's success? Well, it allows predictors that maybe aren't as strong as others a chance to shine. So if we always basically based our new rules on whichever predictor happened to give, say, the biggest decrease in the impurity of the resulting partitions, we'd probably end up picking the same predictor again and again and again. We're going to pick a rule based on that strongest predictor. So if we randomly select just a small subset of those predictors, some of those strong predictors are going to eventually be left out on some of those subsets, and weaker predictors are going to get their chance to shine. So the random forest is able to pick up on some pretty subtle predictors that some other models might have overlooked. So how do we implement it? Well, we need to say how many of those randomly picked predictors are we going to consider. And because random forest models take a while to train, we only are going to select just a few parameters here for mtry. Turns out it's typically not all that sensitive to the value of mtry. So we'll try 2, 4, and 17. 17 is the maximum number of predictors. So we'll try that out too. Basically try the same set of predictors every single time when we have 17. So what are we going to do? Well, we're going to change forest to replace tree here because we're making a random forest. Same formula, same training data. RF is going to be our method, still estimating it with 5-fold cross-validation. And the tuning grid is forest grid. Now, the random forest doesn't care if you center or scale your data. You don't have to standardize the values, but it doesn't hurt. And just to keep the syntax consistent, we will keep that the same. So we'll run it and then we'll wait. So it takes a while for the random forest to be tuned. We're fitting basically for each version of that random forest, I think default is 500 different trees. So it's going to take a while. But we're done, and what we can do is we can say, all right, what does the $results part of the output look like? We'll get the breakdown for an mtry of 2, 4, and 17 that we auditioned, and it looks like that the estimated accuracy when generalizing is the highest for mtry of 4. So here's our standard deviations. They're all basically within one standard deviation of each other, at least the 4 and 17. 2, though, looks to be a little bit inferior. So selected mtry is 4. We could get that out automatically if we just said, all right, go into the results data frame of this object and just report out the row that had the best tuning parameter. We can see how the performance varied with the choice of the parameter by doing plot forest. There's only 3, so not a very interesting plot, but that's what it looks like. The accuracy is its highest when mtry is 4. And then we can start asking, okay, well, how well did it really do on the holdout sample out of curiosity? We estimated the accuracy to be about 95.6%. Notice quite a bit higher than what that vanilla partition does. There's strength in numbers, many, many trees, better than just one tree. We can just find, okay, what fraction of the actual CHURN yes and no's here match up with the predicted values. So the actual accuracy, about 95.3%, tiny bit lower than what we estimated, but that's pretty typical. It's not too much lower, definitely not more than 1 standard deviation lower here, so we are good to go. It's not overfit. And what's going to be the post-resample version? Well, we'll get the same value out, but with kappa as well, if that mattered to us. And we can get the error into the ROC curve on the holdout as well. So once again, looking at the second column of the probabilities that are outputs, we find that the AUC on the holdout sample is a pretty beefy 0.92, which is much higher than this 0.88. So if this forest were to make predictions on someone who in reality does churn and who in reality doesn't churn, there's about a 92.66% chance that the random forest model is going to rank those two probabilities correctly. It's going to give that churner a higher probability of churning than the non-churner. So that's a very good thing. All right, the state of the art in predictive analytics when it comes to building predictive models in business analytics is very often the boosted tree. And the boosted tree, once again, is a whole bunch of trees, but built together in a very different way than the random forest. Instead of just averaging together the results of a whole bunch of trees, what the boosted tree framework does is it builds a sequence of very, very simple trees, all of which are trying to improve on the results of the tree that came before it. So this allows us to go very slowly when we try to learn the relationship. Basically, each tree learns a very small part of the relationship, and they all build upon each other until we've really fleshed out all the subtle interactions and all the interesting complexities of the relationship that we're studying. So with such great power comes a lot of tuning. So there's 4 different tuning parameters. How many trees do we want in our model? So too many, and we might end up with something that's overfit and starts memorizing subtleties and complexities in the relationships on the training data. So we need to figure out what's the right number for the number of trees. We need to tune the interaction depth. How complex do we want each tree to be? Do we want each tree to have 4 splits, 5 splits, just 1 split? How many rules do we want each tree to have? The shrinkage parameter is a very important one as well. How quickly do we want the model to try to learn the relationship? Typically, slow learners are better, so smaller values of the shrinkage parameter are typically better, but smaller values of the shrinkage, smaller values of the learning rate are going to require more and more trees. So there's kind of a three-way interaction going on. If we want large values of the interaction depth, basically have our trees be fairly complex so that we're able to capture very subtle interactions, we need to have a pretty slow learner. We need to have a shrinkage rate that's pretty low, and that's going to require a large number of trees, and that's going to take time. All right, the last parameter, n minobs in node. This just tells us that when we do create a rule for one of these trees in the sequence, make sure that there's at least 10 individuals in the resulting partition once we start splitting up all the individuals into these partitions here. So in other words, make sure that each tree isn't too sensitive to the individuals in that training data here. Averaging 10 is pretty safe, but we can tune this too. We could have it be 5. We could have it just be 1. Each individual, in theory, could live in its own partition. We're going to leave this at 10 for this case. So we'll define our data frame of tuning parameters here, all combinations of these values, in this case 8 different combinations, and let's go ahead and train it. So for this, we're going to add in one additional argument to train, and that is verbose equals false. The reason why is that if we don't have verbose equals false, it's going to print out just a phenomenal amount of output to the console. And that's fine. It doesn't hurt us, but we don't really need a painfully precise narration of what's going on when the training process is happening. So we'll add verbose equal to false just to suppress that. So what are we going to do? Well, we're going to call it GBM. Same formula, same training data. The method is GBM. Still doing it with 5-fold cross-validation. The tune grid needs to be GBM grid. We don't need to standardize the variables. We don't need to make sure they have a mean of 0, standard deviation of 1. This is a model that doesn't care about that, but it doesn't hurt, so we'll just leave that in there to keep the syntax consistently. And the verbose equals false. So we run it and we wait. So normally when we actually tune a boosted tree, we try out a larger number for the number of trees, the interaction depth, the shrinkage, but it's a time commitment. Very often it takes quite a while, maybe an hour or two, to end up tuning a really, really good tree because there's so many different combinations of parameters to look at. In this case, we just set it up so that we can get a result pretty quickly. So it finished, and we can go and look at the $ results. We fit 8 different boosted trees here. We can scan down to see which one's the best. Number 1, we actually see that how we built the tree really matters. Notice the difference in the estimated accuracies of 86% versus 94.5%. That's huge, and it was tied into the learning rate. So the smaller learning rate, quite a bit better. We typically end up seeing that. Here's another set where the learning rate is 0.001 versus 0.01. Same interaction depth, same n minobs in nodes, same number of trees. Notice in this case, though, that we wanted the scratch that and reverse it. We actually don't want a very slow learning rate. We get a much higher accuracy with a slightly higher learning rate. So that's kind of interesting. It turns out that for 500 trees, we actually want a slightly higher learning rate because with a slower learning rate, we're not quite learning all the subtleties quick enough. We're not basically doing a great job of what's going on. All right, so what's the row with the very best results? Well, let's just spit that one out. It looks like a shrinkage of 0.01 is where we want to be. Interaction depth of 5 rules per tree is where we want to be. And about 1,000 trees. That seems just about right. And we get an estimated accuracy of 95.7%. Tiny bit better than the random forest, still within 1 standard deviation, so no compelling reason to think the boosted tree did a lot better in this case. But let's see how well it does on the actual holdout. Just out of curiosity, let's take a look. So what we'll do is match up the actual values with what the boosted tree model predicted. Look what fraction it got correct. We'll use post-resample to do the same thing, and we'll also look at the area under the ROC curve. So on the holdout sample, well, we do a little tiny bit worse than what we estimated. That's pretty typical, but within one standard deviation, so we're not overfit. Our kappa is that if that mattered to us. And the area under the ROC curve, 0.9328. Notice a bit higher than what the AUC of the random forest was. So in terms of ranking probabilities, picking out the customers that have the highest chances of churning, this one's just a little bit better. So we found that the boosted tree might do a little bit better than the other models that we've considered. And one thing that I really like about the boosted tree is it allows us to actually look at the relationships as modeled by the tree. So the way we can do this is to use the GBM command, which is part of the GBM package, so do this manually. And what I like to do is I like to make a copy of the training data set into something called train.gbm. Now, the reason that I have to do this is because I actually have to modify what is inside that column that I'm predicting. So in this case, churn is yes and no. It turns out that the GBM command itself requires those values to be ones and zeros. That's just how the author of the command wanted it. So what I'm going to do is I'm going to change the values in the churn column of train.gbm to be numbers, ones and zeros. So if I take a little bit of a glimpse, I see ones and zeros here, whereas before I started out with just yeses and nos. So once I have that, then what I'm going to be able to do is to use the GBM command. So I'm going to do GBM manual here to fit the tree manually and then to see what some of the relationships look like. So I'm going to fit this on the training data here. The extra parameters that I need is making sure that's GBM here. I need a distribution equals Bernoulli. This is for predicting a categorical response. I could leave that out if I was doing numerical prediction. And then I need to have what the parameters of that boosted tree model needs to be. So what I'm going to do is I'm going to copy these four things, put it in here and say shrinkage equals 0.01, interaction depth equals 5, go on to the next line, n minobs in node equals 10, and n trees equals 1,000. All right, so when I fit this manually, it'll just take a second. But after I fit it, the cool thing is I can make a plot of my gbm.manual, the model that I just fit, and I can say, all right, well, I'm really curious about what the relationship looks like between the probability of churning and maybe some of these predictor variables. So one thing I have to look at is, well, how does the model approach the relationship between churning and account length? So I could plot it, and it looks like, well, there's one additional thing, type equals response, that I want to add in. So I actually get the probabilities out. It looks like that the churn probability gets a little bit higher and higher and higher as the account length goes up. Kind of makes sense after people have been with the company for quite a few days. Then the contracts are expiring. Someone's not going to churn until their contract expires here, so that does make sense. All right, well, what about some of these other predictors, like the number of customer service calls? So number customer service calls. We can see that the more calls that someone has made, the higher the probability of them churning. In fact, once we get into basically 5 or more, there's almost a 50% chance or even greater chance of them churning, at least according to the model here. So kind of interesting. What were the most important predictors? Which ones should we be really looking at? Well, this varemp command we can use on the object that was created by train. So we actually get an idea for which of the variables were the most important. So I can actually go and say, all right, well, let's actually look to see how the probability of churning varies with total day minutes. This was the most important predictor of churn according to the model. And it looks like that once we get up to about 250, this churn probability actually starts to get higher and higher and higher, reaching near 100% at over 300 or so. Now, one thing to be aware of, though, is that maybe customers with total day minutes over 300 are pretty darn rare. So this probability might be sensitive to just a few of those individuals in the training data, but we do see a pretty sharp increase in that probability after around 250 or so minutes. Customer service calls we just looked at. What about total evening minutes? Well, we can look at that as well. And we see the same sort of story. The more minutes that people are calling, the more likely they are to churn. That might make more sense. The more someone uses their phone, the more they're going to be concerned with reception, service, all of that stuff. So if they're not happy at all with the service that's currently being provided, they might have a pretty large chance of defecting and churning here. All right, so the last part of this question says, comment on which model we would choose if we had to go with one of these 5 going forward and why. Do you see any indication of the models being overfit? Why or why not? Well, scanning back, I would like to go with the model with the highest accuracy. So we were tuning based on accuracy. In reality, I'd like to go back and actually tune these based on the area under the ROC curve, because most likely I'd like to use this model to isolate those customers that have the highest chance of churning, so I can send them offers and all that. But I didn't set up my model that way. I was tuning based on accuracy. So I'm basically restricted into picking the model that has the highest accuracy. So GBM had the highest at 95.7, a little bit higher than the estimated accuracy of the random forest model at 95.6. But notice how much lower the vanilla partition model's estimated accuracy was. And then huge decrease going down to the logistic regression, and then also the nearest neighbor model. So am I compelled to go with the boosted tree model? Well, let's just remind ourselves once again of what the standard deviation of the accuracy estimate was at about 0.005. So what we see is this 0.956 that we found with random forest. That's easily within 1 standard deviation of the accuracy estimated with the boosted tree model. So either one is a decent choice. So either random forest or boosted tree are within 1 standard deviation of each other. And so they're both great choices. I'd go with the boosted tree just because its estimate is a little higher. All right, there's no overfitting though, because the actual generalization errors are within 1 SD of the estimated errors, or accuracies. Why don't I change that to accuracies? I think that makes a little bit more sense, because we were tuning and evaluating all the stuff on accuracies. We saw that the actual accuracy for these things on the holdout, it was a little bit lower than what we estimated it to be during training, but it's really not that much lower at all. It's within 1 standard deviation, definitely not overfit. All right, question number 2 talks about the XGBoost model, and it's really the go-to model if you want to squeeze out the last bit of predictive power in your predictor variables here. The problem is that it takes a very long time to tune because there are so many different parameters you can tweak with this model. But this is a strength of the XGBoost algorithm, is that because there are so many parameters, chances are you're going to find an XGBoost model that blows everything else out of the water. It's just a question of how much time do you have and how good and how effective can you be at tuning those parameters. And so what question number 2 does, all the code's provided, it just goes through how you go about making one of those XGBoost models, and it's no easy feat. Be prepared to spend a lot of time tuning those parameters, and so that's why we're going to skip it for this week. This is something for the graduate students if you go onto the master's program, or if you really are dead set on winning a Kaggle competition. This is something you would want to seriously explore. What makes it a little bit better than the boosted tree framework, however, is that XGBoost does regularization. So the random forest, vanilla partition, boosted tree, they choose rules simply based on how well they improved the model on the training data. And we know that that's part of the equation for the generalization error of a model, but there's more to the story. There's the variance of the model building procedure itself. And when we regularize a model building procedure, we basically make it sensitive to how much information it's actually extracting from the training individuals. We know the more information we extract, the more sensitive our model is to the particular set of individuals in the training data, and therefore the higher the variance, the more sensitive the model is to the particular set of individuals that happen to be in our training data. We need to find the right balance between how well the model fits the training data and how sensitive that model was to the set of individuals that happen to be in the training data. And this XGBoost modeling framework allows us to more finely tune that trade-off and to come up with a model that's going to generalize just a little bit better. But it takes a lot of time, but it definitely pays off. All right, moving on to number 3, we're going to dive into the details about what it takes to add a new rule to a partition model. So we're going to imagine the case that we're dealing with a partition that has the following set of individuals. So we have a set of class labels, A's and B's. These are what our model is being set up to predict. We have a numerical predictor X, and we have a categorical predictor gender. So when we develop a new rule to add to our tree, in effect, that's essentially splitting up the individuals in a partition into 2 halves. And the way we do that is to compare the impurity of the resulting partitions after the rule is applied to the impurity of where we started out. Now, there are a few ways of measuring the impurity, and one of which is the entropy. So part A asks us to find the entropy of this partition. So what entropy value are we starting out with? The entropy is a measure of how much information that something has, and there's a formula from information theory that lets us know how to calculate it. So if we head on over to the lecture notes, the slide for entropy tells us that the entropy is minus the sum over all of the classes that we're trying to predict, in this case just A or B, of P times the log base 2 of P. Okay, so how do we get that? Well, we can get P by getting a table of the class labels here. So let's make this a factor of A, B, A, B, B, A, B, and B. So if I get a frequency table of what I see here, I see 3 A's and 5 B's. And if I just divide by the length of the vector here, and in fact, in this case, what I'm going to do is define something called classes, because it's a little bit silly of me to have to type that out twice. Let's let classes be a factor of these A's and B's that we see in the data, too many parentheses. And so let's get a table of classes divided by how many there are. All right, so if I print out what the value of P is, I get the 0.375 for A and 0.625 for B. So 37.5% of my individuals in this partition belong to class A, 62.5% of the individuals in this partition belong to class B. All right, well, I can take P times the log base 2 of P if I use the log command and add in that extra argument base equals to 2. If I do this, this gives me the proportion of individuals in class A times the log of that proportion, base 2. This gives me the proportion of individuals in class B times the log base 2 of that proportion. And the entropy says to sum up those values and then to flip the sign. So -1 times this. So my entropy in this case is 0.95. Now, what does that tell me? It doesn't really tell me anything all that important right now. We're going to use this number to compare to the entropies of the partitions once we implement a rule to see if we got an improvement. So this just gives me a starting point. Now, the Gini index does have an interpretation. The Gini is another way of measuring the impurity of a partition, and the Gini index is simply what the misclassification rate of the random guessing model, what it would be. So if we basically flipped a coin, the coin doesn't have a 50-50 shot of coming up heads or tails here in this case. Because we have imbalanced classes, it has a 3 out of 8 chance of coming up A and a 5 out of 8 chance of coming up B. But we want to make sure our model beats that random guessing model here. The Gini index of the partition tells us the misclassification rate of the random guess model. So how do we calculate that? Well, here I'm going to label that this is the entropy. The Gini, we have a formula for that. It's 1 minus the sum of p squared. So the way that this works out, if you go back and look at the lecture notes here, we have an example for how to calculate this and kind of why it is the case. If you go on to the graduate level program, you'll actually learn how to do a computation like this and figure out what the misclassification rate of that random guess model would be. But for right now, we'll just kind of take that as a given. The value for the Gini index that we get out from a partition is what the random guess model's misclassification rate would be. So if all of the individuals were a member of one class, then P would be equal to 1 for one class and 0 for the others, and 1 minus 1 is going to be 0. It would be 100% accuracy. The idea is that we're going to try to develop rules that minimize the impurity of the partitions. If we measure impurity by entropy versus Gini, we just got to pick one. All right, so because Gini index is a bit more easy to interpret and because it's easier to calculate, we're going to stick with looking to see how well various rules decrease the impurity of the partition based on the Gini index. So part C asks us, all right, if this partition was split using the rule x less than 3.6 versus x at least 3.6, what would be the reduction in the Gini index? Okay, so let's work our way towards that. The reduction. Well, here's where we started out. We start out at 0.46875. In order to get the reduction, we need to figure out the Gini indices of the two child partitions that result. So what I'm going to do is I'm going to define something called left, and left is going to contain the class labels of the individuals who, in effect, would go on the left branch of this decision, the ones who have an x less than 3.6. So the way that I can do that is I can essentially say, all right, a little bit more information here. Why don't I go ahead and define the x values of each of these individuals? Making sure to get my syntax right. 5.7, 7.9, 9.2. I can ask which x is less than this threshold here, 3.6. And that tells me the individuals in the first, second, and third elements are. And if I say, well, what are the class labels of those? Turn on some square brackets and say classes bracket which x less than 3.6. All right, if I look up at the table, here are my three x's that are less than 3.6. I see two a's and one b. But you'll notice once I define this, I get that automatically. Now, why is that useful? Well, guess what I can do? I can define something called p left, which is the proportion of each class in that left partition. So p dot left tells me the proportion of individuals that were A, 2/3, and the proportion that were in individual B, 1/3 in this case. And so my Gini for the left partition is just going to be 1 minus the sum of the squares of those proportions. So I got a value for Gini left. Let's take a look at what it equals, 0.444. And now let's do the same thing for right. So I'll copy, change the name to right here, and in this case, we're looking to see which ones are at least 3.6. And we'll just do some copy and pasting. Change p left to p right. And wherever I see left, I'm going to make it right here as well. So from the table, I see that these are the 5 individuals in the right partition, 4 B's and 1 A. So if I define right, I can see that that's indeed the case. P right, the proportions of each, that looks right. And then Gini right is this number. All right, so what I need to do is figure out, well, what is the Gini index of this split? How do I combine the Gini indices of these two child partitions? Well, I just do a weighted sum. So I weight them by how many individuals were in there. So I can say length left times Gini left plus length right times Gini right. Length left is 3. There's 3 individuals in that child partition. That was the value of the Gini index I calculated for those individuals. And then same thing for this guy over here. So that's my weighted sum. I just need to divide by the total number of individuals that I had. I got to normalize these weights. This is just the formula that I'm going to be using. So this is essentially the Gini index of the children partitions that result when using this rule. So my reduction in this case, well, it's going to be what I started out with, which is that 1 minus sum of p squared here, minus this weighted sum of the Gini indices of the children partitions. So we end up getting a value of 0.102. And if the value for the CP for this partition model was 0.01, the default in R, would this partition be split with this rule? Is this rule good enough? Are the two resulting partitions pure enough in order to meet this threshold for the CP? And we would say that yes, since 0.1 is much, much bigger than 0.01, this passes the test for the rule being worthwhile to add to the tree. All right, now let's look to see if this partition was split using a different variable. So what about the gender variable? What if we split up the individuals based on gender? So in this case, the left partition would be the males, the right partition would be the females. What would be the decrease in the impurity if that was the split instead? And we can make a call as to which the better split is. All right, so we need to do the same sort of process as what we did before. Let's go ahead and update this to be the reduction when splitting on X. And so now let's do the reduction when splitting on gender. Now what we'll do is something quite similar to where we make a variable, I'm going to call it G, to be the genders of the individuals in the data. So male, then 3 females. So male. And then I'm going to just use the rep command, repeat female 3 times. And then repeat male 3 times, then female. All right, so we have our vector of genders. And what we're going to do is we're going to split them into the left partition and into the right partition. And so I'm just going to wholesale copy and paste this command. The only thing I need to change is which classes I'm looking at, not the ones that X where it's less than 3.6, because now I'm looking at, well, which ones are equal to male. And I'll just borrow that down here. Instead of X at least 3.6, the other partition, the right partition, is going to be when the gender is equal to female. All right, so if I do this and look to see, well, who's in the left partition. So if I look at my male class labels, I have an A, B, A, B, A, B, A, B, same thing. For females, I'd have B, A, B, B. Let's just confirm that I get B, A, B, B. I do. So we'll do the same thing. We'll make the probabilities for each of those two classes, the proportions in that left partition, the proportions in the right partition, and go through our calculation of the Gini index. So once we do that, we get the Gini index on the left is 0.5, the Gini index on the right is 0.375, and what we need to do is we need to weight them together. So I'll say Gini children, those are our left and right partitions. Well, remember what I do is I take the length of the vector containing the class labels in the left partition, basically how many individuals do I have in that left partition? I have 4. Multiply that by the Gini index of that left partition, add that to the number of individuals that are in the right partition times that Gini index, and divide by the sum of the total number of individuals. So here's my Gini children. I get 0.4375. So the reduction, and I've gone up here and I've actually defined Gini.parent to be the Gini index of the original partition. I'll take that, come down here. The reduction is Gini parent, where we started, minus Gini children, that weighted Gini index of the two children that resulted, and I get a reduction of 0.03125. So would I add this rule to the tree if this was the only one I was considering? Well, yes, I still would, because this reduction in Gini is still bigger than my threshold. Remember my threshold here, as I said, the Gini index has to be reduced by at least 0.01 to be added to the tree. This one exceeds that, so we're happy we would add that to the tree. But based on the previous rule we were looking at, it's not as good as the one where we split x less than 3.6 versus x greater than or equal to 3.6. So which of these two rules is better? Well, this one, because the reduction in Gini is larger. And this is how the rules for the partition model are built up. The vanilla partition model, the random forest model, the boosted tree, they all do the same procedure. They go through every single predictor variable that's available to them and then figure out all the possible rules that you could develop based on that predictor variable, and it's going to choose the best one when it's considering a partition and how to split that into two. And it'll choose the one that gets the largest decrease in the impurity. So the one that drives those partitions, those children partitions, closer and closer to being 100% pure in terms of all one class or all about the same average value of y, those are the ones that we end up taking. All right, question 4 asks us to do basically the same thing, except for now we're predicting a numerical value for y. And the nice thing is I've actually given you what the y vectors are, the x vector and the gender vector here, so that we don't have to manually type those in. So we're going to do the same thing. We're going to imagine that we have these 8 individuals in a partition, and we're going to try out different rules. We're going to look to see what the decrease in the impurity is using certain rules. And it's a little bit easier when we're predicting a numerical response. We don't have to do a weighted sum of the Gini indices of the resulting children. It's actually a little bit easier here. So let's see how that works. So we start off by looking at the sum of squared errors of this partition. Well, what does that mean? Well, what the sum of squared errors refer to is how far off are the y values we see in the partition from the overall average. So I'm going to define SSE.parent, basically the sum of squared errors of this parent partition here, to be the sum of the squared differences between the observed values of y and the average value in that partition. So here are my observed values. Here are the differences between the observed values and the overall average. Square them up, sum them. That's going to be my sum of squared errors here. So 116. All right, let's audition some rules. So let's imagine that we're going to split the partition, much like what we did before, with the rule x less than 3.6 versus x at least 3.6. So we can see that in the left partition, we would have these 3 individuals. In the right partition, we would have these 5 individuals. We'd calculate the average value of y among these 3, calculate the sum of squared errors with respect to that average, and then do the same thing for the right partition. So we're being asked what the reduction in the SSE is when using that rule. So let's try it out. So let's split up this partition into 2 using this rule. All right, so similar to what I did for number 3, what I'm going to do is to define a vector left that gives me what the y values of the individuals are who are ending up in the left partition, the one whose values of x are less than 3.6. So I can say that those are some elements of y. We'll turn on some square brackets to refer to which ones. Which elements of y am I putting into the left partition? Well, the ones where I find values of x that are less than 3.6. So where do I find that in my vector x? Well, the first 3 positions, that's that 0.2, 1.8, 2.4, We'll take out those values of y, 8, 4, 5, and that is going to be the y values of the individuals in my left partition. And so the sum of the squared errors for the individuals in the left partition, that once again is going to be the sum of the y values of the individuals in that left partition minus the average. We square up those differences and take the sum. So SSE left happens to be this. SSE right is going to be very similar. We just say right. Those are the ones whose x values are at least 3.6. And so SSE right is just going to be right minus the mean of right squared, sum them all up. All right, so we have those defined. And the reduction is pretty easy. We start out with what the sum of squared errors was for the parent, and we subtract off the sum of squared errors among the individuals in the left partition and the right partition. All right, so our reduction in this case is 90.133, etc. And we ask, all right, well, is this good? Well, if it exceeds the value of the CP, then we're pretty happy. So 90 is quite a bit bigger than 0.01, so we would say that yes, or actually, whoop, I misspoke, because this is not the CP isn't how much the sum of squared errors needs to decrease, it's how much the R squared of the partition needs to increase. And the R squared, I need to do another calculation. So the increase in R squared, let's go and look that up. So when we're doing this with the sum of squared errors, all right, so I couldn't find it in the notes, but here is how you figure out that increase in the R squared. So we start out with the sum of squared errors for that parent partition. We look at the total sum of squared errors of the two children that result, and the difference, the reduction, is just the difference between those two quantities. And then what we do is we take that and divide by the SSE of where we started, and this is going to turn it into essentially a percentage decrease. So this is the percentage decrease in the sum of squared errors, which is huge, and it's the corresponding increase in R squared as well. The two are one and the same. So what we would say is that, wow, yeah, this is a very great partition. This rule is very good, the splitting into these two partitions. Yes, we have that this is much greater than the 0.01 threshold that we're using, and so this rule is definitely worth it to add to the tree. Now, what about the one using gender? We split up the partition into males and females. What kind of increase in R squared, what kind of decrease in sum of squared errors, what kind of increase in purity do we get? All right, well, same sort of thing here. We're going to split on gender. And so much like what we did up here, we're going to define the left and right partitions of the first and second child to be not which are the y values corresponding to the individuals with x less than 3.6, but instead the one where we have gender equal to male and where we have gender equal to female. So if I do this, I can look to see, well, what are the y values of just the males? We got an 8, and we got a 12, 11, 11. So looks like it works out just fine. So we can get the sum of squared errors of that child, the males, and the sum of squared errors of the right child, the females. And we can do this same sort of calculation. So the sum of squared errors of the parent partition, where we started out, minus the sum of squared errors of the children. So this is giving us the reduction in the sum of squared errors, and we divide that by the sum of squared errors of where we started. So that gives us a percentage reduction. And in this case, we see that it is a much smaller value. Now, it's still above our threshold of 0.01. It still decreases the sum of squared errors by enough to justify its inclusion into the tree, but it's definitely not as good as making that rule x less than 3.6 versus x at least 3.6. So we still have that the increase in r squared is bigger than CP. So in theory, it could be added to the tree. But the other rule based on x is much better here. So which of these two rules, if we had to choose between the two, is better? Well, this one by a huge amount. And this is because the increase in r squared or the decrease in sum of squared error, or just if we keep it in terms of impurity, the decrease in impurity is much larger than the rule based on gender. And once again, this is how we add rules to the tree. We look at a particular partition and we figure out every single possible rule we could use to split that partition into two halves. And we go through and we calculate the increase in r squared for each rule, or the decrease in the sum of squared errors, the decrease in impurity, and we'd end up selecting the rule that gives the best option, the biggest increase in r squared, the biggest decrease in the impurity. And from a computational point of view, it's actually really quite fast. But that takes us to the end of activity practice lab 9.